So hello everyone, welcome back to this class. In this class, we will cover the following topics. So we'll discuss more about the Bode plots, and then Nyquist stability criteria, which is the other tool which is used to analyze the control system stability. Then Nichols chart we will see, and then finally we will go to see the modern control theory, because as of now what we are covering is classical control theory on the frequency domain. Okay, single input and single output. Okay, related to transfer function. Now when your system become complex and some nonlinearity will come, then it will be very advantageous to use the modern control theory. And also when you want to do some kind of optimization, then you have to use the modern control theory. Okay, so we will discuss something more about the Bode plot. So for example, when you are operating at a very low frequency, because you may ask that why in the last class I have drawn the Bode plot like this, why it is dropping. So when you operate with a very low frequency, let's say this is the input and you may draw the output. So input and output will track, and when you increase the frequency, then again some kind of track aspect. But when you increase frequency more and more, or you increase the frequency like this, then you will see no response in output. So this is the input and this is the output. So you will not see any response in the output. So that means this condition you can mark this point as a this, and this condition you can mark this a point. So when you increase the frequency, because this x-axis is frequency only, right? So when you see drop in Bode plot, because your input and output is not right. So that is how the Bode plot is look like this. So the advantage is Bode plot is it can give you the stability for a stable system, and which is minimum phase. So now the question comes, what do you mean by the non-minimum phase? See, we generally deal with the poles and zero in the transfer function, right? If the zeros are the right half the plane, 1 0, okay, then at least 1 0, then it is called the non-minimum phase. See, generally you comment on the stability based on poles, not zeros. But if any zero comes under the right half plane, then it is non-minimum phase. So, and for unstable also Bode plot cannot be used. It is a misleading information. So in that case, you may use the Nyquist stability criteria in order to comment on the system stability. Okay. So now, in the Nyquist, you may ask, what do you mean by the actually Nyquist plot? For example, if you have a transfer function, any kind of transfer function, you can locate on the complex plane, right? For example, I can locate here minus 2 comma 1 minus 2 plus minus 1i, you can locate. Okay, any complex any root you can locate on the complex plane. Now let's say this is some kind of transfer function. You may say s plus 4 divided by s plus 5. Okay, now you can locate 4 and 5 here, right? 5 is a pole and 4 is a 0, you can locate here, right? I can locate 5, I will locate here, and 4 I will locate. See, I generally circle with zeros and cross with poles. Now, so now this is a point. For example, you may call a 5 plus I, you can say this coordinate. If you put this 5 plus I in this, you may result into the new complex number. So you can plot in a different plane. So this is a S plane, that plane you can say S dash plane. And if you keep repeating this, and when you track all the point, that will be the Nyquist plot. We will consider simple example, spring mass system, right? 1 upon ms square plus cs plus k. This was the transfer function, right? So now it has a 2 poles, right? You can locate the poles. Now the question is, can you draw this in Nyquist criteria for this case, Nyquist plot? You consider m equal to 1, c equal to 1 and k equal to 1, simple case. So you can write this part s square plus s plus 1, this part only, okay? So can you draw this Nyquist plus? So we follow this system. Step 1, put s equal to j omega. This is a step 1, okay? Now in step 2, what you will do, you will rearrange the real part and imaginary part, okay? Real part and imaginary part, okay. See, in this complex plane, in this vertical line, up to where you can go, right? Plus infinity to minus infinity, right? So actually, when you get the complex number by rearranging this, we will see. No, don't worry. Then put omega equal to 0, frequency equal to 0, and get the value, and then omega equal to infinity and get the value. Because you do not put the omega equal to minus, because ultimately second part will be the mirror image of the first part. So don't worry. And in third step, you equate to real part to 0 and imaginary part to 0. Locate the point and finally draw the Nyquist cycle. So what is the first step? So this is your transfer function, right? So if I put j omega, then j omega square plus j omega plus 1, right? So I can write minus omega square j omega plus 1, right? So now I can write 1 minus omega square j omega, right? Simple. Any transfer function you put s equal to j omega. Why s equal to j omega? Because we are dealing with the steady state, not the transient state. That is why the real part is 0. We generally put s equal to j omega, right? What you do in order to remove this j? You multiply by the conjugate and divide by the conjugate, right? So what is the conjugate? This, right? Now what you can add this? 1 minus omega square minus j omega. I can write 1 minus omega square plus omega square. See, there will be no doubt in Nyquist stability if you follow this step. When you see first time Nyquist plot, it is difficult to visualize actually, but it is easy to draw. And then when you draw it, then for you it will not become difficult to understand. Can I go in next step? I will write here, okay? So you take separately real part and imaginary part separate, right? Please check the sign and everything. Okay. I can write 1 minus omega square 1 minus omega square whole square plus omega square and then j omega or I omega, whatever it is, clear to you, right? What is this part? What this part is called? Real part. And what is this part called? Imaginary part. Now in what is the next step? Imaginary equal to 0. Why I am putting real equal to 0, imaginary equal to 0? Because when the plot crosses imaginary axis, real part will be 0. And when the plot crosses real axis, imaginary part will be 0. Okay. If it is crosses imaginary, real is 0. If it is crosses real, imaginary is 0. So that is why we are putting this. Now, if you put real part equal to 0, real part equal to 0, then real part is what? Real part is this 1 minus omega square. 1 plus 1 minus omega square 0. Then omega equal to what? 1, right? Plus minus 1, right? When you put imaginary equal to 0, then what is? Then simply omega equal to 0, right? Then omega equal to 0, right? So now, at imaginary it is crossing plus 1 and minus 1, right? So I will rotate plus 1 and I will rotate minus 1. And this step also you do not forget. I will call it as a step 4. What you will do, you will put omega equal to 0 and omega equal to infinity to check the value of the transfer function. So I will write as a step 4. You put omega equal to 0 and omega equal to infinity and find out the transfer function value. So when I will put omega equal to 0, what is the transfer function value? Tell me. Transfer function is this, right? J omega square j omega plus 1, right? When omega equal to infinity, what is this? What is the value? See, when you put omega equal to 0, it is 1 by 1, simply 1. And when you put omega equal to infinity, 1 by infinity is 0. So you can see here only 1 upon s square plus s plus 1, you can see. When you put omega equal to 0, you will get 1, and when you put omega equal to infinity, you will get transfer function 0, because 1 by infinity is 0. So that means transfer function is 1, then I can locate this point here, right? And finally it will go to the origin. Both the poles are on the right left half plane, right? Stable condition, right? Agree with me? S square plus s plus 1 spring mass system is stable case or unstable case? Stable case, right? So that means the Nyquist circle will go with the clockwise. And what is this point? This point is -1. You should not cross this point. 1 plus GH equal to 0, so GH equal to what? -1. So what is from this -1 to this origin? What is this? Gain margin. So are you able to read gain margin from here? And if you draw unit circle, let's say if it is crossing, you draw unit circle here, and if it is crossing this point, then this is called face margin. So gain margin and face margin. Okay. See, instead of 1 upon s square plus s plus 1, if you take 1 upon s square minus s plus 1, that means you put damping negative. So same graph will be there, but direction will be what? Counterclockwise. So this is clockwise, right? So now easy to draw the Nyquist, right? In step 1, you put s equal to j omega. And in a step 2 only you can calculate this. Put omega equal to 0 and put omega equal to infinity in order to get the transfer function value. And then in step 3 you can rearrange, and in step 4 you may equal to real part 0 and imaginary part 0, and you just check where it is crossing. For example, it is crossing here, right? To find out this value, and you can draw roughly. But this is not the exact one. For example, this can be like this also, this can be like this also, but roughly you can draw the Nyquist plot, right? Because this size can be smaller also, this size can be bigger also. We cannot comment on this, right? We can comment exactly on the intersection point, this point, this point, this point, perfect we have found out. But here, this can be little down, this can be little up, but exactly roughly we can draw, right? Nyquist plot. So see, when I show you this graph, by just without explaining the concept, looks difficult to visualize, right? But when you follow the step, then it will become easy to read actually. Okay. So now it can be used for unstable system, or also non-minimum phase also, and you can see gain margin, phase margin also, and one more concept is a disk margin. So this is the -1 point, right? This is a -1 point. So let's say if it is crossing here and here, then if you draw the circle, so actually you can look gain and phase together, not individually, gain and phase together, then it is called disk margin. Disk margin. So how you draw this circle? See what I said. In order to locate the phase margin point, you have to draw the unit circle where it is cuts, you mark the point. So gain margin and phase margin you locate, and with this radius, if you draw the circle, then gain and phase you can see in one circle only, right? So actually you can comment on the disk margin. That means you look for both gain margin and phase margin, then comment the estimator, not the individual. Because let's say you have a gain margin, but you don't have a phase margin, that means unstable, right? So entirely commenting upon your system stability based on gain margin is not sufficient. You have to look both gain and phase together. Now you can see I have written also. All three shows the gain and phase at each single frequency, right? See, one is Bode, another one is Nyquist, and third one is Nichols. So what you do in the Nichols, the Bode plot between what? Gain, phase with frequency, right? You remove the frequency and you plot gain with phase. That is Nichols in Cartesian coordinate. Very simple. But each three shows the gain and phase at each single frequency. But as I said, Bode plot is misleading for the non-minimum phase and unstable system. Nyquist is useful in this criteria. Already we have comment on this. Easier to see gain and phase together, this margin. I have drawn a circle, right? I have shown to you this margin. Used for unstable system, right? Agree with me, right? In Nyquist, frequency is not shown. That is difficulty actually. Because when I was drawing the graph, you have not seen any kind of frequency, right? In Bode, you have seen, okay, frequency, low frequency, tracking, and then dropping. So actually, you can have some kind of visual, but in Nyquist, you cannot. So that is a difficulty. But if you know how to draw, like I said, then it will be easy for you. And what Nichols chart does the same, but in a Cartesian coordinate and easy to read. See, generally we have a habit to see in a Cartesian coordinate, right? So in Bode plot, if you remove the frequency and you plot the gain and phase, then this Nichols chart, easy to read. Now this is all about the classical control theory. Now we will move to the modern control theory. In frequency domain, it is very important to comment on the system at each different frequency, right? But let's say if your system has a more states, like in aircraft it has a 12 states, 3 velocity, 3 angular rate, 3 angles, 3 position, 12 states, and highly nonlinear system. For example, even if you consider the fighter aircraft, it is more nonlinear, okay, and everywhere optimization is required. So when this kind of requirement comes, then you go and you adopt the modern control theory, okay. Now in modern control theory, that means everything you can write in the state space form, time domain. Are you familiar with this equation? A equal to x dot equal to ax plus bu and y equal to cx plus du. So x dot generally written as a ax plus bu, where A is the system matrix, B is the control matrix, x is the state, u is the control input. So x dot equal to ax plus u is representing the dynamics of the any system. You will see, I will take the spring mass system only and I will rearrange the spring mass system in this form, then you will easily understand. And y equal to cx plus du, y is the output you want to control. So A is the system matrix, generally square matrix, x is the state vector, that means how many aircraft system has. For example, in aircraft it has a 12 states, so x will be 12 cross 1, okay, and B is a control matrix, do not worry, later I will tell you, and u is a control input matrix, and C is generally called sensor matrix, because whatever 12 states is there, you everything you want, you don't control, right? Then based on the C assignment of C, you can take some state from here and you can control. And since output you can also affect, that is why du is written. So do not worry, be with me, all things will be clear to you, right? Consider this simple spring mass system. Mx double dot Cx dot plus Kx equal to f of t. In this, I know that you have a doubt in this, but you don't have a doubt in this, right? No. In a spring mass system, consider one state x1 as a position. So what will be the second state? Can you tell me what is the second state? Velocity. You can consider as a x2 equal to x dot. Okay. So now you can say, you can form a state vector x1 x2, no doubt, right? x1 x2, this part is clear, right? Now when you differentiate x1, what you will get? When you differentiate x1, what you will get? X dot, right? And when you differentiate x2, what you will get? H double dot, right? And what is x dot? You can write as a x2. No doubt, right? Now you substitute this x double dot here. So you can write, I am writing here, okay? You can write m x2 dot plus c x2 plus k x1 equal to f of t. I can write m x2 dot plus c x2 plus k x1 equal to f of t. And what is x2 dot? x1, right? So x1 I can write x1 plus 0 x2. This also I can write. So now in matrix form you can write, you can divide this by m. So what you will get? x2 dot plus c by m x2 plus k by m x1 equal to f of t by m, right? Or you generally call f here, okay? F by m. And second equation is x1 dot equal to x2. I will go back and I will see x1 dot equal to x2, right? I have written. Now see this carefully. See this carefully. What I will do, I will take this x dot part at one side and I will put other things on the right hand side. Now, so I can write here, I will write plus sign here, and I can write minus sign here, and I can write x2 dot. They take this equation, x1 dot x2 dot 0 1. What is the coefficient of this? K by m c by m x1 x2 0 1 by m into f. So this you can write 1 by m in bracket, and then f. If you open this, x1 dot equal to x2 you will get, right? And x2 dot equal to minus k by m x1 or minus c by m x2 and 1 by mf. In matrix form I have written there. What you can say this about this part? A matrix, right? What is this part? B matrix, right? And what is this part? X, right? And what is this part? U, right? And what is this part? X dot, right? So x dot equal to ax plus bu. Clear to you, right? Now here you can comment A is what? 2 cross 2 matrix, square matrix, and X is what? 2 cross 1, 2 row 1 column matrix. And what is B? B matrix. B matrix is what? 2 cross 1. And what is U matrix? 1 cross 1. So now X dot equal to X plus BU you found out, right? General expression. When you take what is the eigenvalue of this? Same as a pole of spring mass system, right? So if you solve this A matrix, characteristic equation of A matrix, then what you will get? Eigenvalue, right? That means poles of the spring mass system, right? So in frequency domain you are commenting like that, and here you can comment like this. Now what you want to control, that decide your Y matrix. Let's say I want to control my position. So what I will write? I will write Y equal to, what is x1? Position, right? x2 is velocity, right? So I want to control my position. So that is why I will assign 0 here, because I do not want to control velocity. I want to control position only. So y equal to what? x1, and here I will put D matrix 0. Let's say in this case output is not affecting by the input. So directly you can write y equal to c express du, right, from this spring mass system, right? What is the A matrix here? A matrix is 0 1 minus k by m minus c by m, right? This is the A matrix, right? K by m, c by m, right? Lambda minus ai is the characteristic. Let's say lambda is the root of this characteristic equation. So you can write, what is lambda minus ai? 0 minus k by m, 1 minus c by m, and here you write lambda 0, lambda 0. So what you will get finally? What you will get finally? Minus lambda, and then 1 minus k by m minus c by m lambda, right? Minus lambda. So now this a minus lambda you have written. Can you find out the determinant of this? Determinant, if you find out, what you will get? Lambda into lambda plus c by m plus k by m, right, equal to 0. So lambda square c by m lambda plus k by m equal to 0, right? What is lambda? Root, right? It is like in this form, right? S square c by m s plus k by m, or you can write this as a ms square cs plus k equal to 0, right? So are you getting my point, what I am trying to say? So this is the spring mass system. In next class we will talk about more. We will take LRC circuit and we will try to explain you the state space modeling, because one is a mechanical example we have considered. Na? Next class we will consider the LRC circuit, electrical example, in order to discuss more about the state space modeling. Thank you so much.